Let's take a look at an example of an event and distribution of outcomes that can be measured using the Poisson and the exponential distribution. So let's start with the Poisson distribution of something that happens 9 times per quarter. So let's assume that for tornado season, we're trying to make a prediction about how many tornadoes will occur during tornado season, say in Oklahoma. So if the expected value might be that we expect to see 9 tornadoes in a quarter. So the question becomes, can I use the Poisson distribution for this kind of event? So is this a systemic issue? Is there any reason to think that there's any dependency between the tornadoes that occur, that there are reasons why tornadoes would happen more at one time than another? So I'm going to operate on the assumption that the tornadoes occurring in a given location and the numbers of them it's a random, naturally occurring event. In the long run, that might be affected by global warming. That might cause me to say there are patterns that have to be accounted for. But in the short run of the yearly data we pick up on tornadoes, I'm just going to go with the idea that there's on average, 9 tornadoes in a quarter in the location I'm interested in. That's a systemic flow, so I'm going to be able to make predictions using the Poisson distribution. So to do that, I lay out my X value of how many tornadoes occur in the quarter, starting with 0 and going up to some arbitrarily large number, which is easily and quickly larger than I would expect to see. But I use that range of values as I go. And then for each of those X values, I look at the probability using the Poisson distribution. So the probability of there being only 1 when I expect 9 is only 0.1%. Again, the formula for that is the Poisson function in Excel. The first parameter is the X value I'm looking for. The second parameter is the NP, or sometimes known as lambda. And this is false. I'm not looking for the cumulative probability. So I've put all these things here. In terms of that, if I come down to the 9, the most likely outcome is 9. That's my expected value. It actually has one of the highest percentages, and it's the peak of my curve. But I can actually see from the curve that if I expect to see 9 in a quarter, I could get as few as 2 or 3, or as many as 15, 16, 17, and that shouldn't surprise me looking at this curve. If I get 0 or 30, that would certainly surprise me, but I do expect to see some variation around that. So again, I might want to look at the cumulative probability function for that. It's the same Excel function, except I put true in the last position to get the cumulative value. So while the probability, if I expect 9, of getting, say, 7 tornadoes is 11.7%, the probability of actually getting 7 or fewer is 32% as I go through. So that's my cumulative probability. So I can make predictions using Poisson about how many tornadoes I can expect to see as things go in. But I don't know exactly when those tornadoes will occur. So given that a tornado has just occurred, what's the likelihood and when will I expect it to happen, next one to happen? Doesn't get answered by the Poisson distribution. That's where I continue my analysis using the exponential distribution. So I might be interested in how many days after a tornado can I expect the next one to happen. So I've said in the past that the scale of the exponential distribution should be the same as the scale of the Poisson. So I'm illustrating here how you can change scale as you go through. I based the Poisson distribution in column B on 9 times per quarter, but I want to be able to discuss how many days it will be between those. So I don't want to measure that distance in quarters or even months. I want to measure it in days. So I'm going to choose a scale of days, and I have to take my lambda. The lambda for exponential has to be the same as the expected value in the Poisson. So if I'm going to change the scale from quarters to days, I have to take those 9 quarters in cell B3 and convert that into a number of days for my lambda. Okay. So the lambda is basically the 9 expected values per quarter divided by the number of days in a quarter, which that itself I do as a math calculation, 365 divided by 4, rather than just using an arbitrary number like 90. So I'm dividing the 9 days by the number of days in the quarter to get a fraction, and that is 0.09863 is the daily arrival rate of my tornado. So if I expect to see 9 per quarter, then I'm really expecting to see 0.09 tornadoes per day. The inverse of that is the mu 1 over that, which happens to be 10.1389. Again, because I did the 365 over 4. If I had just used a 90 for that, I would have had exactly 10 days in the cycle for that. So I've established my parameters to do my work based on lambda. Is this really the same as doing it for the quarterly fraction? I'll come back to that in a minute and demonstrate that it is in fact the same. But doing the daily calculations, I can take my x's. What days do I want to be able to talk about? Again, the mu is going to be on the order of 10, because if they're evenly spaced with 9 per quarter, I should expect to see one happen every 10 days. So about the 10 is going to be my peak. So I can calculate my exponential distribution from this. I'm going to use the exponential distribution function. The first parameter is the x value. I'm interested in the number of days. The lambda, 0.09863, is the second parameter. And I want this to be true. I do want to have the cumulative probability under the curve rather than just the height, because this is a continuous function. So I can do that calculation. I can also take and look at what the probability of having more days than that is simply 1 minus the probability in the column next to it. So that's a very simple calculation. As you can see, it's your standard exponential curve declining over time. So if a tornado arrives on a given day, what's the probability the next one will be 10 days away is 0.627. What's the probability the next one will be more than 10 days away? 0.373. So when a tornado occurs, there's a 62.7% chance that the next one will happen within 10 days, if in fact the 9 per quarter is correct. So what's the probability if I have a tornado that the next tornado will actually happen the next day? According to this data, it's 0.094. Okay, so I've done my distribution. I've even taken it out. So what's the probability if I see a tornado that the next one will occur in 30 days? That's 94.8%. Now again, going back to that main point is important. Is this a legitimate analysis of tornadoes? For the exponential to apply to a Poisson event, you have to be able to say that the events are independent and don't impact each other, that they are more or less naturally and randomly occurring within the interval. On its face, it sounds like tornadoes might be in that bucket. If you were to talk to a meteorologist and present this model to them, they might challenge that to say, well, that's not really true, because the weather conditions that lead to having a tornado are in fact affected by a tornado going through the area. So if a tornado blows through my town today, the high pressure system that pushes it out is probably not very conducive to another tornado. So there are meteorological factors that might invalidate this analysis to say, no, it's not possible to have another tornado in the same place the next day, precisely because there was one yesterday that affected the weather patterns. If that's the case, these percentages are wrong. I really shouldn't be doing the analysis. So before you do this kind of analysis and publish your data, double check it with someone that understands the data you're trying to analyze. The exponential distribution, in fact the Poisson distribution, depends upon these being naturally occurring random variables that are systemically varying, meaning you can't point to a single cause or a subcause or cluster your data in any way. They're simply randomly occurring. So if in fact the probability of getting a tornado tomorrow is unaffected by the probability of getting it today, then the exponential curve fits. But I have a hunch if I talk to meteorologists, they would tell me to discard this logic, that perhaps the Poisson variable for predicting a tornado volume or frequency would be valid, but I shouldn't trust the data on the exponential. But I wanted to illustrate that, because you can always plug the numbers into a spreadsheet, but be careful how you try to sell the results to management. You might be talking hogwash and don't even realize it. One more level of analysis I want to do before I stop, and that is to throw in another sector of data. I've often said you want to make sure that you're analyzing your data in the same scale that it started. So over here, starting in column T, I've redone the exponential data, leaving it in the 9 per quarter mode with a mu of 0.11111. So to do that, it's my classical analysis. I lay out the days I still want to talk about. So I still have the same column I had put in column J. But for each of those values, I convert that back into quarters, basically by doing the reverse math, dividing the number of days by 365 over 4, which was the same conversion I did before for the other data. And then when I take my exponential distribution, I'm actually using that value to get the results. But I'll leave it to you to compare some results that for any x that I pick, I get the same probability both ways, because all I've done is algebraically change the units that I'm working with. I've done nothing in this new set of columns that alters the actual relationship. So you can do either. Probably the safest approach when you're getting rid of it, getting used to it, is to do these two columns over in your analysis. So pick in column U, that's the unit I want to talk about, and then the column next to it is the unit the Poisson variable worked in And I'm safer perhaps if I do that. But if you look, you'll see that the conversion I had to do, the 365 over 4, is exactly the conversion I had to do over here on the first set, 365 over 4. So either way, I have to do the conversion. In the version on the left, I do it once in calculating my lambda. In the version on the right, I've got to do it in each cell in the quarters column to convert the days. But either way, it's the same. It's just an algebraic change. Feel free to do it either way you're comfortable doing it. Will not affect the probabilities.